on that unit 4. Okay, so unit 4, this is basically operational amplifier. And if we talk about operational amplifier, this is an active device, can be used for AC and DC both. Okay, fine. So, and if we talk about uh, the characteristics, this is made up of combinations BJTs. Okay, and its IC number is generally its IC number is IC 741. It's operational amplifier. Fine. If we talk about ideal amplifier, ideal opem. In short, this is known as opem.
Sir, what is IC number, sir?
Actually, what is IC number? Any device, whatever we use here, like this is the operational amplifier IC 741. Have you ever seen black color IC having different pins like that?
Yes, sir, in computer.
No,
Yes, sir.
Yes, sir.
In different electronic devices, this is 8 pin IC with 8 pin IC. Okay, IC 741. And this operational amplifier, I'll let you know how the connections are being performed in this operational amplifier. So in electronic circuitry, we make ICs. Okay, so in this operational amplifier, we encompass this operational amplifier in the form of IC. Okay, and then you can place that IC in any electronic devices so that it can be utilized directly. Fine. So if we talk about ideal op-amp, so this is the symbol for operational amplifier. Okay, this is B1, this is B2, and this is output. Here, this is negative terminal, this is positive terminal. Okay, and two sources are used externally just to operate with this plus VCC minus VCC. Fine. And if we draw the circuit diagram for ideal op-amp, one resistance, this is known as Rin, one output resistance, okay, and this is voltage dependent voltage source plus minus ground. Okay, its value is A VI. A is voltage gain. Fine, voltage gain. VI is input voltage. Input voltage. Fine, and this is output resistance R. So simply, this is the circuit diagram for ideal op-amp. Fine, and if we find several characteristics like So if we make a list parameter of ideal opem and practical opem. Okay, so first parameter that will include like Ri. So for ideal opem, this is infinity and this is very high. This is very high. R naught, and its order is of 10 is to the power 5 mega ohm. R naught is very low, few kilo ohms or few ohms. Okay, and next one is voltage gain. This is infinity. This is very high, of the order of 10 is to the power 5. And one term is CMRR, common mode rejection ratio. This is infinity, very high. Okay, another term is slew rate. Slew rate. This is infinity. This is very high. So keep these parameters in your brain. Like I'll explain what is input resistance, output resistance. I hope you understood the meaning of input resistance and output resistance. You can check it out over here. This Ri. This Ri is having value infinity or very high. So how much current will be going through this terminal? Tell me the value of this current.
0.
Zero. Yes. So always keep this in these point in your brain. This if Rn is infinity, because the ideal op-amp represents infinity input impedance, and the current inside this terminals will be 0 ampere, and output resistance is 0 approximately. So that maximum output can be grabbed at the output terminals. Voltage gain provided by this operational amplifier remains infinity. Okay, and finally, what is CMRR and slew rate? Common mode rejection ratio. CMRR stands for CMRR. This is common mode rejection ratio. Okay, what is that common mode rejection ratio? Let me explain. CMRR is the ratio of differential mode gain to common mode gain. Here AD represents differential mode gain and AC represents common mode gain. And what is the meaning of this differential mode gain and common mode gain? So I was talking like this is the symbol of operational amplifier plus VCC minus VCC, and this is the terminal, and this is the applied input V1 and V2, and this is output. If we define the voltage gain, then it will be ratio of output to the V1 difference to V2. Okay, and this is mod. Fine. So here we are applying the different voltage at input. Okay, and the second case we can consider minus plus. This is output, this is plus VCC, this is minus VCC, and the second case here we are considering that we just shorted these two terminals and we applied single voltage VI, and here the voltage gain will be AP equals to V naught over VI. So here two different inputs are applied at both terminals, and input is considered as difference of both of the applied input signals at different terminals. Okay, while here in the second case we have shorted to two terminals and we had applied a single input on both terminals. So this is called common mode operation. Okay, and this is called differential mode operation. Okay, and this is called differential mode gain. Generally will be represented by 8. Should be very high, and common mode gain should be 0. Fine. So CMRR should be infinity. And next terminology is slew rate. Slew rate. What is that slew rate? This is maximum rate of change of output voltage function of time or over time. Like if I define slew rate, then it will be d v naught over di, and it's maximum rate of change of voltage over time. This is called slew rate. In the case of output opem, the slew rate must be infinity, and in case of ideal opem, the slew rate must be. So these are basic terminology utilized for ideal opem and opem, practical opem. And one more thing, like if I draw the characteristics of ideal opem, this is input voltage, this is obtained output voltage. So you see, in the case here we are applying two terminals, two operational voltage. These are two operational voltage, VCC and VEE. Okay, you can also call it minus VEE. This is called linear region. And generally we use operational amplifier in this region. Fine. And furthermore, this region is called saturation region. Okay, this is called saturation region. Is that fine? Yes. I don't think there is so much difficult task to understand this all terminology. This is the basics. So if somebody asks you, you always keep these points inside your brain, these 5 points, 6 points, 5 points. Because many times whenever you appear in interview at the different places and different companies or different PSUs, government organizations, research organizations, so anybody can ask what is the input resistance of operation, output resistance, voltage, CMRR, slew rate. In fact, the definitions can be asked by you, and this equivalent circuit, they can ask you to draw this equivalent circuit of ideal op-amp. You must keep all these things in your brain forever. Okay, and these short definitions, and this is the characteristics you must keep inside your brain. What is the characteristics of open, and what are the different region of operation, amplifier operation? Fine. So you must keep all these things inside your brain so that you can compete somewhere. Now talk about that inverting operational amplifier. Okay, so here I was talking about inverting operational amplifier. If this is V naught, this is plus VCC, this is minus VEE, and I was talking about one more thing. Before going on that inverting amplifier, I would like to explain something about feedback. RF, and this is RF. Okay, and this is VI. Let me explain something about feedback. What is that? Here, this is plus BCC, and this is minus VE, V1, V2, and V0. This is open loop, opem. Okay, and if we utilize this opem in some configuration with some biasing, so and we apply this resistance. Okay, fine. If we apply this resistance V0, V1, V2, and this is resistance. This is called feedback resistance. Feedback resistance. I hope you understand the meaning of this feedback. Okay, this is called feedback path. Feedback means, you remember?
Explain again.
Why you were sleeping? Fine. Like this. Okay, this circuit. So this is called open loop configuration. This is open loop configuration. And if we apply one resistance here between input and output, okay, so this resistance creates a feedback path. You can see feedback means, I hope you remember already what is the meaning of feedback. If we take a portion of output and we apply it at input, we connect with this with input, and it is called feedback path. So here this resistance RF is applied to create a feedback path. So this is called closed loop configuration. Closed loop configuration. Okay, one more thing I would like to explain over here. Like, what is the meaning of this? If this feedback can be of two types. First one, negative feedback. Second one, positive feedback. Okay, and how we can define in terms of this negative and feedback in terms of this opem? Let me explain. This is negative terminal and this is positive terminal. If we take output, a fraction of output, and we connect this fraction to this negative terminal, then this is called negative feedback. If feedback path is connected to negative terminals. If feedback path is, if a fraction is taken and then it is connected to positive terminal, this is connection to negative terminal. This is connection to positive terminal. Okay, so here I'm explaining. This is plus VCC, this is minus EE, this is output, and you can see this is negative feedback. This is configuration 1. Okay, 1. And here the second configuration I would explain, like minus plus, and if you take output, fraction of output, and you apply it at positive terminal, so this is positive feedback, and this is plus VCC minus VEE. And generally, you know what is the difference between positive feedback, circuit with the positive feedback, and negative feedback? You see, if we talk about negative feedback, then this circuit is called amplifier. Okay, and if we apply positive feedback, then this circuit is known as oscillator. Okay, do you know what is the difference between amplifier and oscillator? Anybody? Let me explain. Amplifier means if we apply, okay, let me take another page. Amplifier,
Correct?
all the participants are requested to keep themselves on mute. Amplifier means if we are having any device, we are applying input, we are applying input, and we are applying input like that. Okay, and if we get output, and if we get output like that. Okay, and here if this is the amplitude A1, here this is the amplitude A2 of signal 2, and here at A2 is greater than A1. So amplitude of signal is increased, while frequency is constant. If frequency is F1, frequency is F2, and F1 equals to F2. So this is amplifier. Okay. Second one is oscillator. What is oscillator? If we are having a system, any device, we apply some input or without input. We just make it functional by plus VCC or minus VCC, and we collect some output. Okay, in that case we find oscillations, sustained oscillations. We find some signal like this, like sinusoidal wave, cosinusoidal wave. This is oscillation.
But sir, what change did it make to the input signal, sir?
Input signal, you just trigger it. Okay, like if you apply some input, if you do not apply, then it will start working. Like oscillator means clock frequency. Generally we generate the clock frequency, like okay, you will understand the meaning of this clock frequency and all the things in the future. Currently you just try to understand this. We just try to generate this kind of oscillatory signal to sustain oscillation. Okay, and oscillations, that is fine. Oscillators. Okay, and here in case of amplifier we apply negative feedback. Keep this, remember always. Many times the question, and here in case of oscillators we apply positive feedback. Always we try to keep this, remember. Many times this question is asked in different interview examinations. Like if we apply negative feedback, then which kind of device we can generate, or amplifier utilize which kind of feedback, either positive or negative. So we will speak of that negative feedback. Or oscillator, positive feedback. Okay.
Yes.
And so we were talking. Yes.
So what is going to happen for the frequency for oscillator, input frequency and output frequency?
Output frequency we can generate in our manner. Okay, input, I told you that if we do not apply input as well, we can get output. We are just having some two operational voltages, plus VCC, minus VCC. So if we do not apply input as well, then we can get output. Fine, but output frequency we can set in our way. How much frequency we need. Fine?
Okay, sir.
So here, okay, one more terminology I just want to explain. This negative terminal, if input is applied on negative terminal, fine, here your output is applied on negative terminal of opem, fine. So this is called inverting amplifier. So this is inverting configuration. inverting configuration. Why this is inverting configuration? Let me explain. Why this is called an inverting configuration. Okay. So can you tell me how much is the current here? Tell me how much is the current I? Zero.
Zero, sir.
Brilliant. Yes, exactly. And why?
Ra is infinite. Resistance is infinite.
Exactly. You are brilliant, guys. And how much is the current inside this resistance? Tell me.
Which resistance, sir?
This resistance. R.
Sir, nahi.
Zero again, because this is
Why?
open circuit. This is infinite input resistance connected here, but this is infinity means open circuit. Okay, if this is open circuit, so no current will be passing through this terminal. So this I becomes zero. Suppose this circuit is going having current I1, and this circuit is having this branch is having current I2. We have KCL at node A. Apply KCL at node A. So here I1 plus I1 equals to I2 plus I, and I, you know well, it is 0. So furthermore you can say that I1 equals to I2. Fine. I1 equals to I2. And one more thing. Can you define how much is the voltage at node A?
It's VI.
VI. Why? This is having resistance. This branch is having resistance in between VI and this node A.
VI minus RI.
I minus I1 into
I1 or I?
Okay, let me make some circuit for more simplicity. This is feedback resistance. This is Ri. This is approximately infinity. This is R. This is Ri, and this is Rf. This is V naught, and this is Vi. And here this is open circuit. So now tell me, what will be the value of voltage at node A? This is node A. Can you comment on this voltage? How much is the current? This current is 0. If this current is 0, then I into R, it will be 0 volt. So here it should be 0 volt, na? Yes or no?
Yes, sir.
Yes. Okay. And this is very interesting phenomenon. So let me explain this phenomena. This is known as virtual short or virtual ground. Virtual short or virtual ground. Like you see, this is very interesting phenomena, minus plus. And here this is RF, this is RI. You see this current is 0, and this is resistance R. So you see how much is the voltage at this point? V equals to 0, VA equals to 0 at this node. And how much is the voltage at this point? If this is B node and this is A node. So we already know BV equals to 0. So whatever is the voltage at this node is directly being represented at this node A. So voltage at node B equals to voltage at node A. Okay, so and why this is happening? Just because of this open circuited terminal. If this terminal is open circuit, Rn equals to, because Rn equals to infinity. Because Rn equals to infinity, so whatever is the voltage at this node B, same voltage will be there at this node A, but polarity will be opposite. It will be, if it is minus, then it will be positive. If this is minus, then it will be positive. Is that fine? Yes or no?
Yes, sir.
Yes. He will be changed.
Which one will be changed? Polarity will be opposite. Okay, and that's why we were able to define that minus terminal and positive terminal.
Okay.
Because of that, Rn equals to infinity, and voltage at node B equals to voltage at node A. So you see, this is practically, this is behaving like open circuit. Practically, A to B, this A to B is open circuit, but ideally, but virtually, not ideally, virtually, A looks, A seems shorted. Virtually, it seems like that. This is very important point. If you just want to finish out full operation of this opamp, you have to understand the meaning of this. Practically, A and B are open circuit. You know where, because this is infinity. But you see, virtually A seems shorted with B. Means whatever is the voltage at point at B, this is like short circuit connection. Seems like this is short circuit. In the case of short circuit only, this voltage will be similar, huh? VB equals to VA. Is that fine?
Yes, sir.
Yes, so that's why this is known as virtual short or virtual ground. So if somebody asks you what is the virtual short and virtual ground, so you will directly say the node at voltage B, at node B, the voltage at node B will be equal to voltage at node A of opamp in closed loop path, and specifically it is practically this is open circuit, but virtually it seems like shorted. A seems like shorted with B. So this is called virtual short condition or virtual ground condition. Why virtual ground? If VB equals to 0, then VA will be 0 as well. If VB is grounded, then VA will be seen as grounded. It will be like if VB is grounded, then VB will be grounded as well. So virtual ground as well. I think there is a difficulty in this concept. Okay, so here we were talking about KCL. Okay, so this node, the voltage at this node BB equals to voltage at this node BA just because of virtual short. So if this is BB equals to 0, then BA equals to 0 volt. Just because of virtual short or virtual ground condition. I hope this is clear to you. So we can say that now we can apply KCL at this point. What is the value of current I1? VI minus 0 over RI. And what is the value of I2? 0 minus V0 over RF. So can we write this like? I1 equals to I2, and this is VI minus VA over Ri equals to VA minus V0 over RF. And what is the value of VA equals to VB equals to 0. This is just because of virtual short or virtual ground condition. So VI minus 0 over RI equals to, this is 0 minus V0 over RF. So here you can see V naught equals to minus Rf over Ri into Vi, and this is the output voltage of this first inverting amplifier. Why this is called inverting? Now you will understand the meaning of this term. You see here, this is very important. Whatever the input you have applied, okay, you are getting output but with opposite sign. If you apply positive input, then you will find negative output. Like this is like if this is opem, okay, and if you are applying input with this polarity, then output you will collect with opposite polarity. Okay, so here just because of negative sign, output is of opposite polarity in inverting amplifier. Okay, so that's why this is called inverting amplifier. Like if we are applying input at negative terminal, then it is called inverting amplifier because polarity of output is opposite. So here we can rewrite this definition. If input is applied on the negative terminal of opamp, the output is achieved with opposite polarity. So this is called inverting amplifier. Keep this, remember, keep this inside your brain forever. Because polarity is changed, inverted. Polarity is inverted, so that's why this is inverting amplifier. Okay, so keep this inside. And this V naught over Vi, this is called AB equals to minus Rf over Ri. This is closed loop gain minus Rf over Ri. Okay, closed loop voltage gain. Second one I would like to explain. This is non-inverting operational amplifier. Non-inverting operational amplifier. This is minus, this is plus. This is minus. So in the case of inverting amplifier, we were applying input at negative terminal, but in the case of this plus minus, this is Vi. Non-inverting amplifier, we are applying input at this negative, positive terminal. Okay, so this is the difference between inverting and non-inverting amplifier. So it totally depends upon if we, whatever at which terminal we are applying the input voltage, whether this configuration is inverting or non-inverting. Fine. So there are two kind of amplifier: non-inverting amplifier, inverting amplifier. If we apply input at negative terminal, and this inverting amplifier we apply input at positive terminal, that is called non-inverting amplifier. Okay, fine. And one more thing. This terminal is known as inverting terminal, and this terminal is known as non-inverting terminal. I hope you understood the meaning of why this is called inverting and non-inverting terminal, because we apply input and out is that which is achieved with the opposite polarity. So inverting terminal, if we apply input at positive terminal, we find output with the same polarity. So that's why this is non-inverting. So this is all about the basics of this operational amplifier. Now we'll perform the operation of implement the devices using operational amplifier. Now tell me, how much is the current here? I
0.
0. And similarly, how much is the current here?
0.
0.
0,
Yes.
sir.
0. Okay, so what is the voltage at node B?
VI.
VI. This is VI. Brilliant. And what is the voltage at node A?
0.
minus
Sorry, sir.
What is
VI.
the VI?
minus
Exactly. VI. Simply VI. Polarity, it will grab by itself. Yes, simply it is VI. Okay, so suppose this is current I1 and this is current I2. If we apply KCL, sorry, so it will be I1 equals to I2 plus I, and this current is 0. So find this I equals to I1 equals to I2. And what is the value of I1? This is 0 minus VA over Ri equals to VA minus V naught upon Rf, and VA is VI. Ri equals to, this is Bi over Rf plus V naught over Rf. So here V naught over Rf equals to, this is minus, sorry, this is minus sign. So this is minus, so it will be plus and it will be Vi 1 upon Ri plus 1 upon Rf. So here you will find final expression equals to like Vi on Rf equals to Ri plus Rf over Ri Rf. Rf will be cancelled out, so V naught will be equals to Vi 1 plus Rf over Ri. This is the output voltage of this operation, inverting operation. If you say same polarity, whatever you are applying at the input, same output. So that's why this is not inverting. Okay, this is same polarity, and this is AB, voltage gain equals to V naught over Vi equals to 1 plus Rf over Ri. This is the voltage gain of non-inverting amplifier. I don't think this is very difficult. This is very easy. Okay. Now, next point. Differential amplifier. Okay, now we are moving towards the application part of this operational amplifier. How we can implement different kind of circuitry. Minus plus. This is V naught. This is, suppose we are applying V1. Okay, this is Rf, this is Ri, and here we are applying another voltage Ri. This is V1 and this is V2. Fine. So let me explain the operation. What is the value of this current? 0.
0.
Okay. What is the value of node voltage VA?
0.
0.
No, sir, V2, sir.
V2, yes. Yes. So if this current is I1 and this current is I2. So suppose at A, we are applying KCL. So here I1 equals to I2, and here directly I am applying V1 minus V2 over Ri equals to V2 minus V0 over Rf. Fine. So again I can solve this terminology. V1 over Ri minus equals to V2 1 upon Ri plus 1 upon Rf and minus V0. One more configuration. This is the voltage. So VA equals to VB just because of virtual short or virtual ground, and this current is 0. So this I1 and this is I2. This current is I3 and this current is I4. This current is 0. So here at node A, I1 will be equals to I2. At node B, I3 equals to I4. So at node A, if we see, then in that case V1 minus VA over Ri equals to VA minus V0 over Rf. This is equation number 1. At node B, then V2 minus, I can write VA or VB. Okay, it totally depends upon my choice, and equals to VB minus 0. Okay, over Ri. Fine. VB minus 0 equals to Ri. Equation number 2. I can find the value of this V2 or VA or VB. Okay, I can put this value VA or VB from this term. This is also VA. This is also VA. I can find the value of VA. Let me check it. That V2 over Ri equals to VA, and this becomes 2VA upon Ri. 2VA upon Ri. Is that fine? Ri will be cancelled out. Then it becomes 2VA. Fine. Now VA equals to 2. This is V2 upon 2. You put this value here, and after this, if you will solve this problem, then definitely you will find that V0 is V2 minus Vi. Okay, is there any problem?
Okay, sir. Thank you.
And you can apply the condition like you can apply the condition Ri equals to Rf as well.